Hello everyone, today we will discuss about the Z-plan analysis. Outline of this chapter is introduction, then mapping between the Z-plan and the S-plan. Then we will go forward to jury criterion. Number 4 is a steady state error, and in the end, conclusions. Objective of this chapter is a mapping between the Z-plan and S-plan, transient analysis in the discrete time, and the jury stability criterion and steady state error. First of all, we will see some revision about the S-plan. For the continuous time signal, the closed loop transfer function may have the form of the TS, such as the polynomial equation about the numerator and the denominator. And we know the order about the numerator all the time should be or equal to less than the order about the denominator. We can rewrite this one or factorize about here. We put the sum 0 and we have a sum pole. And in general, partial friction decomposition of the step response can be rewritten by the following about this. Imagine if you have a transfer function s plus, for example, alpha I, this one you can write the sum of the first order or sum of the pole equal to the 0, or you have a second order or higher order system. And we saw that in the EE312 for the higher order system you can change to the first and second order system and solve the problem, and you can see some error exists, but you can neglect about this error. However, in this course we will be mainly deal with the step response, and we consider about the first order and the second order system. With taking the Laplace inverse of the system, you can find the first equation will be C1, second will be di and E alpha I, and this one depends about the denominator equal to the 0, bigger than 0 or the last 0. You can change to the sinus and the cosinus. In general, you can write the GIER real system ZIT, cosinus imaginary ZIT, and the sum about the sinus. And in the S-plan, we consider the pole in the which part of the plan. If the pole stay in the right half of the plan, your system complete become unstable. If it become in the left of the plan, your system become stable. We saw together, if the pole exactly become in the J omega, your system become oscillations. And if pole from the origin part start to going up, your system become the high frequency. From here they go to the high frequency. If you compare about the figure number 1 and figure number 2, you see the oscillation will be higher, that means the frequency will be high. And if the system from the original part go further than original part, you see your system become settling time is different, or settling time become the better. And if the pole exactly in the real system or real axis exists, we have the ideal system. And if you go further than this, settling time become better, or system become faster response. Here in the left side, your system become diverged. How about in the discrete time? In the discrete time, you can write the differential equation such as here, just only change the S to Z. And we use the same rule. The order of the denominator should be less or equal to order of the denominator. If you factorize, and you will find the Z plus Z1, Z plus Z2. This is the 0. This is the in the Z domain. Before I use the S, here I put the Z, and here the name of the number of the pole. And we will consider here the first order and the second order system. And by taking the inverse Laplace about here, C1z become a step, and here become alpha ik, and if you remember here again delta equal to the 0, delta bigger than 0 and delta less than 0, you find a combination about the sinus and the cosinus. But the area in the Z transform, you have the circle around origin part and the radius is 1. You can rewrite the complex number by the RIEG theta I. RIEG theta I will be in the Z domain. This will be theta, and the Ri or R is the radius about, for me, the circle about the origin part. And if the pole be outside of the circle, my circle is this one, your system become diverge or unstable or unstable. If the pole exactly will be on the circle, your system will be oscillate, the same as thing that in the S domain, when the pole will stay in the j omega, here will be on circle about my 1. Your system become oscillated. Inside of the circle, your system will be stable, if you see. And if theta increase, for example from here and from here, the theta increased, I put theta 1 and theta 2, the oscillation will be higher, that means the frequency will be bigger. Theta 2 is bigger than theta 1, that means the frequency about here, if you see the figure here, will be more than the theta 1. Okay. Then if become in the origin part, depend about the inside or outside. Inside the system become stable, outside become unstable. Start to come close to origin, the transient part, the settling time will be faster, or your system become faster response. You see from here will be oscillated, T settling time will be less, and settling time very fast and close to origin part. And here the table, he said, you can write the Laplace domain in the discrete time, and what is the Z transform? The Z transform about the 1s or step in the Laplace domain become a step of the KTS. Z transform becomes Z minus 1, or will be 1 minus Z minus 1. 1s plus A, here you can write the E minus A KTS, or here you can write Z minus E minus ATS, or you can write 1 minus E minus ATS Z minus 1. The ramp 1 S2 in the Z domain become TS Z minus 1 power 2, or if you multiply by the Z become Z minus 1 minus Z minus 1 power 2. And here will be sinus E minus A K T sinus omega T, and we put in the sinus formula, or I can write the E minus A Ts Z minus 1 sinus omega Ts upon of the Z minus 2 E minus A Ts minus 2 E minus A Ts Z minus 1 cosinus omega Ts plus 1. This is the table for the Z transform and the Laplace domain. Here the same thing. Now mapping from the S-plan to the Z-plan. Any point in the S-plan I put in the transfer function about the Z equal to ESTS, I can go to the Z-plan and you will see the origin part. The red part that my system becomes stable exactly in the left half of the plan, and the right part, the yellow part, become outside of my circle. My system will be unstable. That means if you have any point, for example s equal to 2, you put here, you find some point in the yellow regions. If you put s equal to -2, your system, by this transformer you put equal -2, you go inside about the circle, or etc. Now we will compare about the system we explained as before. If you have a lot of point here, what happened with the transfer function to go to the Z plan? In the Z plan you find a circle about the such as the region about the 3, the line 2 will be circle about 2, and the line become around 1. What's the difference between 1 and 2 and 3? If you remember, from the 3 you go to the 1, the settling time will be better, or from 1 go to 2, 3, settling time will be increased. From here the same thing, from 1 to 3 you go, settling time will be increased. If you check about the line from the 1, all of the point you put in the transfer function here, you find the line in the Z domain, something like this. That is a circle actually, is here, and with the different about the theta. And from the line 1 you go to the line 5, frequency will increase, and here we explain from theta 1 we go to the theta 2. Theta 2 is bigger than theta 1, and the frequency will be increased.